0 means a piece of cake. 0 meant piece of cake.
Oh, really?
You didn't listen.
Yeah, I didn't.
100. Okay, 100. Got it. Yeah. Decrease. Decrease. Okay. So now that we're kind of got their ducks in a row here, I see some of us are writing down. This is something we did not do, Monday on the kinetic molecular theory. It just basically is talking about the characteristics of gases, and you're probably already aware of these. Do you know that gases have low density? Okay, they float.
Yes.
Yes, we already knew that, but now you know why. It's because they have very, very, very few grams per liter. So density is, in this case, density is mass per volume, but for gases, it's grams per liter, because they take up so much space. So we just call it a liter versus a milliliter. So that's one thing you already know. You know that you brought your box of air. You brought it. Where's your box of air, people? Okay, compress it. Compress it. Okay, so smush it together, right? So you can smush your gas molecules together, because there's a way that you can decrease the space between the molecules, because you can compress them. You can also relieve your pressure and let the gas kind of expand, and that's your box of air expanding, because you can increase the space between the atoms. Who's ever heard of the word diffusion? Biology, right? What does it mean, Jake? So if I brought in a box of Krispy Kreme donuts, those scent molecules, they're trademark.
Oh, yeah.
You know,
It's
scent molecules.
It's
So
like
what happens?
with like perfume or like deodorant, where it just like goes into the air. And
So what's that word when it goes into the air? It diffuses, right? You're trying not to use the word, but you can use the word.
Yeah.
It diffuses into the air, right? So there's this great formula that kind of represents how fast they move, and it's this right here. Because basically particles, they have energy, right? And if they have high amounts of energy, that means they probably can actually move really fast. So Ke represents kinetic energy. Good. So the things that move fastest are the things that weigh the least. So M and V here, what do you think M stands for? Mass. V stands for velocity. Look at it. I'm pointing up here for you, okay? So here's velocity. So things that move really, really, really fast are probably really tiny. So give me, what's the molar mass of oxygen gas? Oxygen gas. 32, because it's diatomic. So, no. So here's our oxygen gas is 32 grams per mole. Carbon dioxide? Ready when you are? So 44-ish, 44 grams per mole. Okay. Which of these babies are going to move faster? Oxygen, because they weigh less, right? Think of a football player. If I'm the center, probably not going to be, I'm probably the big guy, not going to be running. My brother was a tight end. It's like this all the time on the side, looking down the line. He's a little skinny guy. Flying.
That's the wide receiver.
That's a wide receiver? Tight end can do the same thing, right?
Well, yeah, but they're more.
Okay, well, he was also on receiver. He also ran down for a touchdown. Go, catches it, lands on his elbow. Arm comes out of arm.
Oh.
And so he couldn't play anymore. Not for a while. He got back into it. But, yeah. So he was a little guy. He was going to go flying down the field. Yeah, so the people in the center probably are not going to be flying down the field. So basically, high velocity means you have lower mass, because at a specific temperature you have a specific amount of kinetic energy. The other term we're going to talk about more so tomorrow is effusion, and effusion is just basically what happens when you pop a hole in a balloon. What happens? It pops, but maybe if you just put a pinhole in a balloon. Right, so it's basically the escaping of gas through a tiny hole. Yeah.
Is the V and MV squared velocity?
That's velocity. Yep, velocity. So I put VEL, velocity. So we know what diffusion, effusion is going to be more of a specific scenario. On your foldable, there was one that was called Graham's law of effusion. We're going to hold on off on talking about that till tomorrow. We're going to talk about Dalton's law a little bit today. But basically, I'm going to give you guys time to practice on the laptops eventually the kinetic molecular theory a little bit more. So we'll get there. But before we even touch that, let's talk about the scientific gas laws. Okay? Pull out 1 through 5. 1 through 5. We have like 3 things we need to tackle today before we go into our simulation. The first one I want to go over is number 3. Let's start easy. Did we all get this BC right? I'm waiting for more yeses. Yes? And if you did not, you need to write it down quickly with me. Okay? So the BCE, when it says when we're producing ammonia, that's the synthesis of ammonia. And the synthesis of ammonia means to come from what? It's elements, right? So from nitrogen and hydrogen. Okay, it looks like some of us did not get this done. You better be writing fast. I'm expecting that you at least have your givens down. So what are your givens here?
48.6.
Okay, so we have V. We have V for volume. What else do we have? Temperature and pressure, but these need to be converted to
Kelvin
in atmospheres. Oh, hold on, let me cover that up. All right, you should get 283 Kelvin and 0.7 atmospheres. Thumbs up, you got that far. Okay, so if you're given T, P, and volume, and V, and the question is how many grams of nitrogen are needed to produce blah, 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 what are we actually looking for? What's our first question? Raise your hand. Yeah.
Are the amount of moles?
Right, so we're looking for N. We're looking for N for moles of a gas. Well, which gas are we given all this great information about? Ammonia. You've got to read between the lines. It says how many grams of nitrogen are needed to produce this many liters of ammonia at that temperature and that pressure. So it's talking about ammonia, right? So when we find all this information, it's going to be about ammonia. Then we actually have to use the BCE and go back to nitrogen. And how do you go back to nitrogen? Ratio, mole ratio. So we're bringing back the stoichiometry stuff that we so love, and BCEs, okay? So this information we're going to use to find N of ammonia, and then we're going to use stoichiometry to go back to N for our moles of nitrogen. Okay, so tell me what to start with, guys. I'm depending on you. PV equals nRT. You're going to solve for N, and I like to denote who I'm talking about, and this is ammonia in this case. With me, time. So PV equals nRT. Rearrange this to solve for N. PV over RT, and then plug, 0.70 atmospheres. V is 48.6 liters. R,
8.
atmosphere, liters per K, mole K, okay. And then temperature, 3 Kelvin. Okay, what cancels? Everything but what? Everything but moles. We're looking for moles, right? We should have said it correctly. And Suzanne, tell me what you got.
1.46 moles.
1.46 moles. Fantastic. And this is moles of ammonia. Just to be clear. So you just write it there just so you don't forget. All right, and then the question is regarding nitrogen, right? So let's get back to nitrogen. Jalen, tell me how to get back. Tell me how to get back from ammonia to nitrogen. I hear you, but tell me specifically what to do. 1 point, I know, but you can do this part. Tell me how to get from ammonia to nitrogen.
1 mole of nitrogen.
Where are you getting your 1 from? Right, from BC. I hear you. And then what goes on bottom?
The 2 moles of ammonia.
Right, so it's a 1 to 2 ratio. So you're going from 1 to 2, or 2 on bottom, 2 moles of ammonia on bottom, 1 mole of nitrogen on top. Ty, give me the next step. My question was to get to grams of nitrogen.
The mole of nitrogen is
PTOE.
14.
yeah, I don't have one.
14.
Okay, so 14 times 2 is 28, right? So 1 mole of nitrogen on bottom, 28 grams on top. So moles cancel. Yay! We're getting to grams of nitrogen. Anybody? How much? 20.44. I'll go with 20.5. 20.5 grams. Add all this junk in the middle. Hold on. There we go. This process is the Born-Haber process, which is a way that we make ammonia. We can actually reverse this process and make nitrogen, Where would nitrogen be useful? FFA. Where would nitrogen be useful? Say again? In the soil. You have to make nitrogen to give to plants so they can take it in and then we can eat them. Right? We need nitrogen for what part of for what biomolecules? What biomolecules? Remember we got carbs, lipids, proteins, and nucleic acids. Which one's gonna have nitrogen? I hear it. Nucleic acids and proteins. Good. Just a little biology review just every now and then. Okay. Let's choose one more. Yeah. Choose one more and think about it. Which one is the best one you want to do? 2 is what I'm hearing. 5. 5. Okay, let me start with 2 and then I'll go to 5. 2. Okay, so this one's actually giving us a little bit more information, right? So we've got magnesium. Did you get your BC right? You gotta, if you read that it's hydrochloric acid reacting with magnesium, then you would say those are 2 reactants. You make hydrogen gas, right? And we're dealing with gas laws, right? So what has to be produced? Gas, right? If not, we've done it wrong, right? We have one job. We're at BC first. Okay, so after you get your information about your grams of magnesium, your hydrochloric acid, you're like, oh my gosh, she's giving me information about 2 reactants. What kind of problem is this? If I give you information, data about 2 reactants, and you don't know who to start with, limiting reagents. Your favorite ones? Remember? How'd you forget those? Okay. So that's why you're like, how do I start this one? This one's hard. I gave you guys some hard ones to really challenge you, but you'll have a lot of knowledge to use for the easier ones because I will not give you something this hard probably on your test. I gotta double check. Okay, so grams of magnesium, stuff about hydrochloric acid. You got temperature, pressure, and volume. Okay, so what's the percent yield, the student's percent yield? It says the student's capturing that volume. What are they capturing though? Which gas? Hydrogen gas. So you got to be picking out the pieces. You're actually looking, you found the volume, the actual yield of oxygen gas. Okay, so that's V, volume of oxygen. So what are you going to do? Find the theoretical yield of the oxygen so you can actually do the percent yield. So what's our first question? Is like, all right, what's the volume of oxygen theoretical yield-wise that we can make? But before you can actually figure that out, what do you have to figure out about the reactants? How much you have of them, right? So you can figure out which is the LR. Okay, so oops. Some of us remember a bit more from last time than others. So here's my setup. Here's my grams of magnesium, molar mass. There's how much I have of magnesium, 0.047 moles of magnesium. You can get to half of that. That's easy molar mass. The second one you probably forgot a little bit about. Do you remember volume and molarity? Smush them together. What do you get? Moles, thank you. You guys are a little bit on the dead side? That day off? Throws you off? Okay. I had a massage. Okay, so 0.015 of a mole of hydrochloric acid. Okay, do we feel good about getting to the halves of both? Shake your heads, something. Okay, you can get the half of both of those. How do you figure out who your LR is? Raise your hand if you're good with this. How do you get to LR? I'm going to call on somebody if I don't get a volunteer. Hayden? Kara, 2 brains. Ratio! What ratio? The mole ratio! Okay, I'm going to go in green. So, if this is how much I have magnesium, what's my mole ratio between magnesium and hydrochloric acid? SBC is a little bit on the messed up side. There we go. 2/1. Thank you. So 2 moles of hydrochloric acid over 1 mole of magnesium. So what is this? 0.094 moles of hydrochloric acid that I would need. Okay, tell me right now who's my LR. If I need 0.094, and I have this hydrochloric acid, right? I've got way too little. I got 0.015. I need 0.09. That's crazy. I need a lot more. So this one's my LR, and this one's my excess. Okay, so what was the goal of that? Danielle, tell me why we need to find the LR. Now it's going to help you. Theoretical yield. So we can find the yield, right? So what am I going to start with? Limiting reagent. Half of it. Okay, we're struggling a little bit. How much do we have of it? How much do we have of it? Okay, so you're starting with this, and you're going to figure out how much you can make of the hydrogen gas. Then we're actually going to do gas law, okay? Promise. Then, so we're doing Stoich chemistry on the front side of this problem. The last problem we got on the back side. So it can be before or after, yeah.
How do you write up why do you have to get the limiting reagent first?
Because, okay, so we're given all this information about the gas, right? About the volume. So we're given this volume collected, we're given temperature and pressure, and it's all about that hydrogen gas. But I'm not given any information about the hydrogen gas other than the actual yield. So when you find percent yield of it, that means I have to get theoretical yield. So how do I get theoretical yield? It's the la land on paper, calculating from the LR how much I can make. So that's why you have to get it first. So from here, you have to find theoretical yield from the LR. So I'm going to start with my hydrochloric acid, which is not a gas, go to gas, and then plug it into the PVs on our teeth. Okay, so we're moving on this one, guys, and then we'll move on because I want to make sure we have time to practice our other stuff. So 0.0150 moles of hydrochloric acid. You guys have your LR. What's my ratio?
1 mole hydrogen over 2 mole HCl.
So 1 mole hydrogen gas according to the BCE. Remember, this is BCE. And 1 mole of HCl. So this gives us 0.015. So same number, but proving to me it's the gas now. Okay, 0.015 moles of hydrogen gas.
2.
Is it 2?
No, HCl.
My bad. So double check the ratio. My BC is up high. You guys have yours in front of you. 1 mole of hydrogen gas to 2 moles of hydrochloric acid.
Yeah.
Yeah. Oh, I didn't. This is right. Yeah, 2 to 1. Okay. So here, this is our N, and you have to get to a mole of gas, or N in gas, because it's the PV auxiliary, which is regarding a gas law. So then, what variable are we going to hunt for now using the gas law? The volume, right? So we have N, we have P, we have T. We're looking for V. So PV equals nRT. Let me get myself some space here. PV is nRT. Solve for V.
NRT over P.
Okay, so divided by P on both sides. So V is equal to nRT over P. And then I'm assuming you can plug. What's your volume? Anybody? Maybe you got that far? This is a tough one. Yeah.
I got 0.19.
What number is this, 2? Yeah. 0.189 liters. Is that what you said? Approximately. Okay. This is liters of hydrogen gas. Ooh, doggies. This is theoretical yield. What do I do from there? Hannah. Who's Hannah?
Actual yield or theoretical yield?
And what the heck was actual yield again? We've gone through all this problem. What was actual yield?
149 million.
Right, you see it right there. Student captures 149 milliliters. That's the actual yield. That's what they've captured. Now, we're going to capture gas tomorrow. It's like capture the flag, but chemistry. 149 milliliters of oxygen gas over that, but I can't have it in liters, right? So what do I do here? Because I have this one in milliliters and I have the same unit.
So can you just do
Yeah, you can convert this to milliliters. That's fine. I mean to liters. We'll just do that. I'm good with that. Either way, whatever floats your boat. That's actual yield. This is theoretical yield times 100. Somebody tell me if they're a good chemist. What is it? 78. Would you want them on your team? Yeah. I mean, they're not bad. They're like a little below our desired, but they're not bad. They're yeah.
Why is it changed it into the hydrogen? Why is it the same number?
It was just, I didn't fix that. That's 0.07. My bad, because the ratio is 1 to 2 now, so it's 0.0075 moles. Thank you. Okay, yoga, stretch. Let's get this lung capacity up. I'm asking for a tree right now, people. Tree. Okay, and breathe. Okay. welcome back. Let's stop stoichiometry for a moment, okay? We need to kind of practice the theoretical stuff, which is the kinetic molecular theory. Go to my website. Go to Unit 5 Docs. Hold this at your desk because I need to see a lot of your other work before we continue to checking number 5. When you go to my website, go to Unit Docs. Everybody's computer should be pulled up at this point. Yeah. What? Okay, thumbs up if you're on my website, and you're to Unit Docs, and you're on Unit 5, and you see simulation. Some of us are there. Okay, if not, then it's pretty intuitive. When you click this link, it's going to ask for you to download this PhET activity. And PhET is a really cool simulation, which uses the kinetic molecular theory, and it simulates gas particles. Because, I mean, I don't know about you, but I can't see gas particles. Can you guys see them? Look really hard. Still don't see them, okay? So this is going to kind of simulate what it looks like. This is kind of what it looks like when you pull it up, okay? So it's like, pump the handle, pump the handle. What do you think you should do, guys? Pump the handle. All right. Oh, look at all the gas particles. There's so many. I can keep going, but I'm not. That's not the simulation calls for. The simulation calls for this. Okay, so it asks for you to go through it, draw a couple of things first, and then go to the simulation. Okay, so you're gonna draw some things first, then go to simulation. One pump. Don't go crazy like I did. One pump into the gas to talk about what happens to the particles, and then so forth. It's pretty straightforward what you're looking for, okay? If you would like to, you will have to write this on your own paper, okay? Draw your little boxes and all. If you want to work with a partner, that's fine. I'm going to give you guys about 30 minutes right now, and then we'll see where we are, okay? If your interwebs is not working, there are 4 desktops. Jacob's claimed 1. Spread out. The worksheet, yes, you do need to look at the worksheet underneath there. The worksheet is there. Okay? Disperse. Leave your foldable, leave your gas stuff on your desk. Leave your foldable, leave your gas stuff on your desk.
2G, like 3G, that's what I like 4G. I like 4Gs on 5Gs. Oh, there it is.
If you want to do one person has a simulation, pull up, 1 person has a custom, pull up,
Follow the simulation. We're just both doing We'll draw a diagram which is 10 gas particles. These dot proportions.
Guys, if you want somebody to pull up the simulation, somebody to pull up the document, it might be easier, okay?
Whoa. So how many dots are there? I didn't see them. They're all close together. There we go. Wait, we're clarifying. Got it. Wow, look at how fast they're moving. I feel like having high pressure. Really fast, you know? Oh man, that's even faster. Oh.
All right, take about 25 minutes from here. We're gonna see where we are, okay? Teamwork made the dream work.
Oh yeah. You know it. So we need long arrows and everything. And maybe a couple of they're happy they all share the same name. When you realize that they're not perfect. That's right. What happened if the fantasy seems to be? What do I have for fantasy? Down 2 weeks. Very confused, right? Try to pick the blade keep your light elevated. So low pressure is like shorter air.
You can skip around some too if you find a part later on. You're like, oh, I really want to try that. That's fine. I know you're excited.
Yeah, you can. I love science. 26 hours of homework a night. High volume move slower. High volume, yeah, they're not close. So I'm not sure what the speed would be, but they're not close, so they're much better. So it's just normal size. One thing these slow is if it's high volume, is it slow? Do they move around some?
No, the volume is what makes them move slower. It's just like pressure.
They're spread out.
They're spread out because they don't hit the
Yeah. So do we not need air? The low volume is smaller square.
The low pressure, basically, you see
What happens if you use the pump to gas? I'm doing pumping a handle, pumping a handle. That's all the way to the top. I have more particles. So what happens to the clump? When the temperature increases, you can bring down the freezes. Then it starts over reset. Okay, so it increases 0.5 APM. No, 0.0. Okay, so it increases the temperature and the pressure. But don't boost, like it's pushing on. Two. It's a fun question. Keep your eye on one point. How many points do you move straight lines? It's random. Do the pressure stand constant speed? I can't tell. Oops, I broke it. They move around faster for the light species. What? They move around faster for the light species. Yeah, but yeah. Super sloppy, sorry.
Okay, cool. I'll do it with my mom being fine. Just want to make sure you guys
Do they keep it like constant speed or they keep it constant speed? So watch what it looks like. No. It looks like they move like it's slowing down faster. Yeah, they move faster. So they're exchanging energy. Yeah. So no. And then like
try to push that stuff more. I'll try to do more at the end of the class.
So like literally with other atoms. Or the wall. Always move in the same direction. No.
Never mind.
Not because they don't change. Collisions. PCBs. Oh, wait, never mind. CDs. CD. The thing. AC buttons. Using the setting on the right side for 100 heavy species. Allow the pressure to stabilize. Record the pressure. Okay, heavy species, we're going out. Remember we don't go on to raise the hour. Okay, so put 100 heavy species. We're going down.
Alright guys, you should be moving on to the simulation. Stop on part 1 where you're drawing and move on to the simulation. I want you to see more.
Are we doing the pressure? Yeah, the pressure. The pressure is around 0.98. Allow the pressure to stabilize. Right now it's at like 0.5, 6. What are you doing? You're allowing. Right now it's at like 0.5. Check that out. 0.55. I broke it. Look at this. Look, the thing came on. Almost flew off into the sky. Yeah. Return back. Yes, these can just release together gas. Record the number of heavy species to 0, and the lights are lost in the room. There you go. Fly out. Whoa, what do you want to choose? On B, 2. Wait, there is no energy. That is what it is. That was for the heavy species. And then few slight species people. See, does the mass of the particle significantly affect pressure? No. Let's see. C is no because the pressure is very dynamic. Yeah, thank you. Okay, D. Oh, yeah. Like, gotta be the 100 of the heavy species and the light species. We just did that. doing it again. Pressure is rising. Oh, it's only at, oh, it's rising. 4, 5, 5. I say 0.5, 0.5, 3. 50 of the white species and no hidden species. What species will here? 100 T lights. Wait, no. Only 50 white? Yeah. 100. So this is 0.2. G, 50 light species, 100 hidden species together. Together. 50 light, 100. Bang. It's crushing. It's going up. 60s. 75. It almost fell. 75. You lost pressure. 64, 163, 163. Lost pressure. Oh, well. How does this compare to the pressures from 3 and 2 before? You combine them together. Yeah. Combine pressure is less. Oh, combine. No, not combine. Oh, but it's right here. Those two added together equals 75.2. That's a lot of what? Because just half the pressure. You only do it once. Not enough to happen. And lots of gravity. Okay, what do you think? The resulting pressure from C. The resulting Consider 0.05. Yes. If you do too much, the lid was actually what pressure gets too much. A and B combined. Okay, here we go. So, temperature's constant. 200 Hz. No, watch out. I broke it. Oh my gosh. Did y'all watch out? What's happening? You said. There we go. You have 200. Constant parameter select temperature be constant plus 200. Oh, there's no question. What no question at all. Use a little man to change volume. What happens if the pressure is low? Right now it's at 20 at 1. Like the little man doesn't push this thing. The pressure increases a little bit. So the pressure rises. Volume goes down, the pressure pressure goes up. See, this is a inverse. Bang. 6. Playing around with another species. You just did that, so we're going to minimum of pressure. Minimum of pressure over 7. Yeah. Minimum, is that 7 species? How much volume? Minimum of volume. Wait, how much volume species? I'm doing 3 species, 100. No, how much volume? How do you tell me? I'm running out of 3 species. How much volume? I'm saying 100. I don't know these species in the minimum of volume. Oh, you only need 100? I think these would be 50. No, I'll do it 25 plus. Oh wow. Pressure. 50 bushel. No, 25 minimum of volume plus 25 species. Okay. Number 7. I think $1 boxes of not always long. Great. I think. Yeah, because deals with volume and pressure. Yes. So volume, lower volume, higher pressure. So, will they be closer? Yeah, they'd be closer. And the high volume guys.
Why is the temperature changing now? Matt, how do you make the temperature constant?
You press constant.
I did.
Press temperature.
I did break it. I love
Hit
it.
reset. When you let it all go, the temperature changes. So low volume and constant pressure. Pressure. High pressure? Low pressure? No, I mean second. No, high volume. What? Come look.
What is temperature? I'm just changing the ice. And the ice is making it. Why is the ice making it hotter?
Ice is not making it hotter.
Well, it's got ice coming out of the bottom and the temperature's going up.
What? This one?
No, we didn't change it, but it's like creeping up.
We're like, we put the temperature at constant and then we're changing the volume.
So, what volume?
The little hand. The little hand.
Oh, yeah, that's right.
See? The ice is spot on. I know where the temperature's
Because lower volume and lower temperature are related. Because if you lower the volume, they're still going to be colliding with the same speed, right? And if you're colliding at the same speed, the pressure is going to go way up. But you can't let the pressure go up because that's not what the simulation in this case is supposed to be happening. So it's slowing them down by cooling them down. There's a reason. Oh!
Oh, it broke it.
Thanks. Didn't see that. Capture the gas.
That was like part 1? Oh no, part 1 feeling. What? All of them?
I have light species to it too.
So part 4. So Charles will deal with the stuff.
So many gas particles.
The other thing. Pressure must be pressure and number of moles. 200 heavy
You
species.
should be on leave for 2 or 3, guys. Stick around some.
Okay, there's 200 heavy species in the container on a constant parameter box in the top right. Select that the constant should be pressure. And 200 heavy species. Bang. The constant is now pressure. Volume is changing. Why is he running away with heavy species? What temperature?
No temperature's going the same.
There's 200 heavy species in the container on the box in the constant. Okay. Heat the flame at the bottom to heat up the container. 9. Temperature at the bottom. Add.
Temperature number of moles per minute.
Why can't this stay at? There we go. Temperature. The volume stays the same
With the number of moles.
and just keep going up. Yes. Oh, the pressure's going up. Here we go. Here we go. They're moving faster. Oh. So what happens to the volume as the changes?
The volume
Oh,
for 8, volume gave a constant.
no. It's still stuff.
B.
As temperature goes up, volume goes up. Wait, something was supposed to happen.
Temperature goes up, the volume.
Something was supposed to happen.
Yes.
You have to change the volume.
This guy ran away. Let's put it back. Oh.
Oh. He's moonwalking.
So as heat goes up, as temperature goes up,
Volume increases.
That's crazy.
Oh no, so 9A is volume.
Yeah. And then since the volume increases, then
I'm gonna want to
direct
read it for watching.
and as temperature goes up, this is a direct relation.
Well, that's C.
Yep, direct. Play around with temperature of light. What combination do you need to blow the top off? You need like 2,000 degrees. Okay, ready?
I'm almost running out of height.
Ready? Bang. Watch it, watch it. I'm gonna put it at 2,000 exactly. Oh, okay. It's 1 I don't know what's flying those. How do you tell
How do you tell the volume?
So 2,000 degrees.
See, what's happening? Why does this keep happening? Look at this. What's happening? Why do we do this? Why is it going out? Hurry up. No, it's nothing more. I think, oh, gravity blocks. No one wants gravity.
Ah, that was nice. Why don't we just keep going? Immediately. Bang. I got two. Alright, so then, something I really know is for you. Okay, 1,000 minimum, so 1,000 Ks, and the minimum of volume.
1,000 K.
I feel like it's like 10,000 or maybe
11. Diagram from
Alright guys, finish your last thing. I want to talk about some of these as at the end. Take about 2 more minutes to go through the simulation. It's okay that you don't finish, but I want you to explore.
So, first one would be trial plot is trials
Trials for G volume.
So, low would it be high temperature versus low temperature? And would it be low volume?
The small one is
The small one is low temperature.
yeah. And then just the trial is watching it affect the cup.
I think it was 5 volume, 5 movements, 5 Part 5, we got Dana Lusac. Dana Lusac. Dana Lusac. The pressure and temperature, so volume is good. Yeah, 11. I am on part 5. Now I'm on 12. On the constant parameter paths in the top left, select the appropriate constant. Like, did you get 11 constant? And that's flat. Oh, yeah, volume. Okay, so the constant parameter paths on the top left. No, it isn't. Yes, it is. 11? Yes, it is. 11 is Virginia. That's number 12. We were talking about the guy, skating thing. Did you 5 cents? The constant parameter paths. Okay, so it's 200. Bang, look at all those speeches. Those are the pressures and temperature changes. So I need to heat the flame. Heat the flame. There's the pressure setting. The pressure increases. Bang. Pressure increases. 18A pressure increases. Yep.
Alright guys, I want you back in your seats in 1 minute, okay? 1 minute, bring your chair.
As the temperature goes up, the pressure goes up. Upwards down. C dot. So C, this is A. Do everything else? 14. Oh, wow. So last question? What was that last question? Oh, let's see. Let's get it to time degrees.
Are you 30 seconds come back to your desk?
I want to see how much temperature I can get. Yeah. So about 2,500 K.
You have 20 seconds come back to your desk.
30 or 14? 14. Yes. I'm gonna finish. You said, yeah. Max, we're gonna finish. No way. What's we doing? You just say shut up and I'll make it the last one. Okay, so we need I-10 a lot of pressure, really good.
Hi, I didn't see your stuff. I'll come back, okay? Okay guys, so go ahead and stop looking at the simulation. Just minimize your window so you're not distracted for a moment. Minimize your window because I know you want to finish, but just give me some time here. Minimizing mine, have a lot of stuff in mind. There are 2 questions on here I want to talk about, okay? So here we go. Under the one where you had 2 different partial pressures. You had heavy particles in there and you had light particles in there. What were your pressure differences, Jacob? How much? From like the heavy particle one, it was like 0.3, 0.38, and the light particle one, 0.34. So very, very small difference, right? And I think you did it too. You had like a 0.02 difference. So what that was supposed to be indicating to you is that it was a very small difference, which is probably not that significant. And the reason why is because heavy particles, when they hit the container, they have a large amount of force with them. But are they moving very fast? No. So that kind of offsets a little bit because they're not moving as fast. Light particles, they're not hitting with a lot of weight on them, but they're hitting probably faster because they're moving faster. So the force differences there is based off the weight of it and the speed of it. Well, heavy particles move slow, but light particles move fast, right? So they kind of offset each other, but they still have approximately the same pressure. We just didn't run these over like, 14 hours to see that the pressure differences were very, very minimal. But you guys did see they were fairly minimal. So not as significant as it could be. The other one was, you probably did not get it this far, but as the temperature goes down, the volume goes where? So as the temperature goes down, what's happening to the particles? They're slowing down, right? They're slowing down, but you have to keep the pressure constant because this is Charles' law. So what should the volume do? It should decrease as well because Charles' law has a direct or indirect relationship. Direct. So whatever happens to the volume, same or temperature, same thing happens to the volume. So hold on to this for me. You will be turning this in on portfolio check day. We'll have another day where we get to kind of finish up a couple of these. Okay, so don't lose it. Okay. I'll think about it. Okay, so the last thing we need to go over is Dalton's law, and I'll go over number 5 if I can at the end of class. Let me go here. Let me go over Dalton's law, and then I'm gonna do one more stoichiometry problem with you. This is non-mirror foldable. Basically, it's adding, right? So I want to see your eyes up here and on your notes. So just kind of minimize your window. Actually, go ahead and log off right now. Go ahead and close out your windows, log off, and then shut the top of your lid as you're kind of copying down what you need to here. I know I'm trying not to make you multitask, but the computers in front of you are distracting. So I'm trying to get them out of here. Dalton's law. Because you will see this on number 9 on your PS14. So when I say finish most of all these books are in the way, but I'm going to read the words to you. Homework. Finish most of PS14. Okay? Finish most of PS14. There's Graham's law in there that you will not be able to do yet, but I want you to try every other one, specifically the stoichiometry ones. All right, I'm seeing most computers are closed, meaning that they've been logged off. If only after they've logged off, you should close them. Only after they've logged off. Okay. So Dalton's law is just a simple addition of partial pressures. So partial pressure means that it's not all the total pressure, but a bunch of little partial pressures together would equal the total pressure. Just like all of us together, we weigh something, right? So if I added up everybody's individual weights, we'd have a total weight. So we have time. But partial pressure works the same way. P total equals PA of one gas, PB of another gas, PC of another gas, and so forth. It just depends on how many different gases you're adding up. It's a very simple formula. So, what are all the gases in the atmosphere? Ty, what's one of them? No, don't tell me yet. Somebody give me one. Nitrogen. Give me another one. Oxygen. Give me more. Give me more. Water vapor. Give me more. Traces of argon. Got it. Okay, there we go. That's pretty much what the atmosphere is made of, right? So if I know the total atmospheric pressure, I would say P atmosphere equals P of nitrogen plus P of oxygen plus P of CO2 plus P of water vapor plus P of argon, right? So that's a long one because there's tons of gases in our atmosphere. But it could be something relatively simple like in an experiment we're going to do tomorrow, we're going to be collecting gas over water vapor, over water with an upside down graduated cylinder. Remember that drawing? We're going to do it, guys. I know, upside down graduated cylinders. Who would have thunk? So we're going to have to actually add up multiple pressures. Yeah. What does it do? Nothing. It's just chilling. It doesn't. It's very inert. It's unreactive. Okay, so that's Dalton's law for you. On number 9, before I forget, number 9 on PS14. Here's what I need to tell you. Just make a note for yourself. Because I forgot to put the partial pressure of water vapor in the problem for you. So here we go. PS14, numero 9. Partial pressure of water vapor is 3.73 kPa at 27 degrees C. That's a given. Okay, that's on number 9. It's a given. And let's just do number 9 together. Here we go. Number 9. It says, and if you have your PS with you, pull it out, you can look at it. I'm going to read it to you. A chemist, collects a sample of nitrogen sulfide gas over water at a temperature of 27 degrees C. The total pressure of the gas that has displaced a volume of 15 milliliters of water. So some gas has displaced water. That actually is not relevant on this point. But the gas pressure total is 207.33 kPa. What is the pressure of the H2S gas collected? So basically it's saying I collect this gas over water. And when I do that, water kind of gets kicked up into the atmosphere, so it makes water vapor. So what are the two things that are making up total pressure in this case? water vapor and that gas. There we go. So this is P total. P total is equal to P of this gas and P of water. Which of these do we already know? No. We know this one, right there. I just told it to you, that was a given. I forgot the number 9. And so what are you going to do? Subtract. That's it. Dalton's law. Whew. I think that's like a 3rd grade problem right there. It's just how to interpret the question more than anything. So that's how you do number 9. Yeah, that's it for problem set 14 right now. Let's do a stoichiometry one because this is where we are on that struggle bus. Stoichiometry. The limiting one. Is that, hold on, let's start anew. Let's start fresh right now because I can always check number 5 tomorrow for you guys, with you guys. Potassium chloride decomposes. Strike this right on your givens. We have like 15 minutes left in class.
So BC.
Okay, BC, I want you to start this one by yourself. I'm giving you 2 minutes to get started. This is fresh. It's nice to give you a fresh one so that you're really trying to figure out how to problem solve. Okay, so what's the first variable you know you're going to be solving for? Have we gotten that far? Pressure's given.
Is it in? Because it gives everything.
Okay, so we have everything but in. So what is in referring to then? Moles of what? Lies! Of what? A gas. I'm saying that really loudly to strike your attention because you should be asking yourself, is this stuff I'm finding, is it about a gas? Yup. Is this a gas? Nope. What's the gas? Oxygen. Because it's decomposing, right? Remember, gas laws are all about gases, and that is the big, and I say it just every day I can because that's the biggest mistake people will make. I was in your place at one point, okay? I remember struggling and saying, well, how do I know what this is? You just gotta read, right? So you got 2 here, 3 here. You got P of 755 millimeters of mercury. What's that in atmospheres? Anybody? Give me when you get there. A little less than 1, more specifically preferred. Calculators! Divide by 760 millimeters of mercury. 0.9. Okay, I'm stopping there. Okay. T is 23 degrees Celsius, so that's 296 Kelvin. V is 0.0426 liters, so I'm going to go ahead and put in my P equals an RT kind of lingo here. And the question is how much grams of potassium chlorate decomposed. But Lizzie said we have to find N before we can backtrack from gas to potassium chlorate. So N of O2 is our real first question, because that's what we don't have, and then you can backtrack from there. So N of oxygen, just to specify it's about a gas. Which gas? O2. And then plug, 0.99 ATM. Have you started dreaming about the R value yet? Oh, it'll happen. 0.081 atmosphere liters per mole. Okay. And okay. Anybody want to mentally calculate that? It's like that's like point. Let's see, 0.1. So it's like 20 8, so that's 28-ish, and that's about 0.05. So what's 0.05 divided by like 28? It's gonna be like 5 liters, or 5. No, is it gonna be like 5 moles?
You said 0.05.
I know that's 0.05 divided by 28. What is it? I'm waiting.
Okay, guys.
What is it?
I got 0.0017.
You know, thanks though. N was what? 1 said, I forgot to put my decimal back. Okay, so this is moles of oxygen gas. Okay, then what do I do from there? What's the ratio? It's on your paper. 2 moles of KClO3 to 3 moles of O2. And then that cancels, yep. Sorry, I'm doing it for now here. And then I'm going to grams of potassium chlorate. So 1 mole of potassium chlorate is like 122.5, if I'm remembering correctly. And that's like I don't know. 7? What's the, no, how many grams is that?
7.
I don't believe you though. Grams? How many grams is that? How much?
What is it?
I will make you mental math if you don't tell me the answer.
How would you do that?
You would do like, okay, so like this is 3 decimals over, that's 3 decimals over, so that's supposed to wash. That's about 1.
If you add them all together.
So 0.66. I don't know.
0.1.
What is it?
0.420, please.
What is it?
I got 0.1421. I don't think that's right.
I swear. What is it?
It's really
0.1.
small.
1.21 grams. Okay. That's good stuff right there. I'm stopping there.
It's almost 7.
Yes. It says how much though. How much potassium chlorate must have decomposed. So it did ask for that. Because whenever, shh, be quiet for me.
Because it gives you the O2.
Right, because it gives you gas information, and it's about that gas. It's just your job to figure out which gas it is, which is oxygen, which is the only gas in this problem. And then from there, you're like, I got moles of gas. I don't have moles of the solid that was decomposing. So you have to backtrack just through stoichiometry. Okay, so we have a couple months left in class. We also going to do the deflate gate.
Tom Brady.
Tom Brady, since the Colts lost, you know, and whatever. So this is something we might get to later, but basically it's like the ideal gas law. What would have happened if they still don't really have a whole lot of confidence in their answers, but it talks about how you can use ideal gas law to prove that there was gas leaked to make them win, blah, 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 blah. So,
Tom Brady just paid.
other than that, I'm going to stop for now. There's a couple minutes left. I can pull up PS14. I want you guys to do something. If you have PS14, keep working on it. If you don't, then you pretend to do something. You do not pack up yet. I will ask for the first group of girls here to go put their laptops up, and then we'll kind of go in rows. We'll go in heaps.
I used to do the economics, the GOGs. I would sit there and tie,
PS14.
tie, huge and stuff. It's unridiculous nonsense.
We still have 7 minutes left of class. Yes, we're going to go. That'll be as easy. I have like
I can give you Oh, really? Can you though? Can you? Are you sure that I'm doubting you very heartily? Get it? Heartily. I'm still doubting. I see nothing. For your word that you exactly what I meant to happen. Now you don't know what's going on. And you Yeah. That's what we don't get like control. So you 4.2 liters pressure is 2.8, volume is 1.8, pressure is 1.2, volume is what? V2 equals Q1 over Q.
Not, oh, you're talking about the year? Yeah. Oh. A couple, okay.
There's at least 15, 16 together, 17 by itself, 18 by itself, 19 by itself.
V2 times equals V1 times V1 over
5, 6, that's like 6. Yeah.
Not too bad.
Zachary, is that what you got? Was that the question? Number 5. Alright, the group of tries, go put your laptops up.
Hey, what's up? We tried very hard.
Thank you. I got you. Okay, that's what I got too. I don't know why I've never fixed on there.
How many problems have you had?
Talia, thank you.
How many weeks are left?
We have like at least till like
Like 7?
no, like 6. Like we're on 14 right now.
Don't rush.